This is a recording for the setting up the RC circuit, and so obviously you need a battery and a capacitor. Connect that in here. There we go. Okay, here when I put it on here, I'm going to make sure that the negative side of the capacitor is facing the negative side of the battery. Put a large resistance in here. And a switch. And then connect. And now I would be, ready to measure. And here, with the voltmeter on both sides of the capacitor. And now, oh, it's already a little charged. There's a very quick discharge. Just connect either side of the capacitor. It's quite discharged. Okay. Then turn this on, measure the time, measure the voltage every 10 seconds. And at this point I'm just going to use this as showing how the RC circuit is set up. I'm not actually going to take measurements. I'm going to stop this here for now. So this is what disconnect the battery, and in order to discharge it, connect across here, and then again turn it on and measure the voltage every 10 seconds as the capacitor is discharging. Then putting in the other capacitor just the same way, and here I'm going to quickly discharge this capacitor here completely, and maybe it shows up on the video that it really went down to 0.0. Again, make sure that the negative is facing the battery. And then, of course, do the same thing as before. Charge. And then when you're done taking the data, then taking measurements for two capacitors in parallel. So put them parallel to each other, but still in series with the resistor, and here hook up the voltmeter, and then of course for discharging, again connect here. I don't know if I actually have enough pieces here to do that. Barely. There we go. And then in series, and that negative is here, and connect everything again. The voltmeter would have to be connected from the net. So the only way to do that is this way, and charge, measure, and then discharge, measure. So they are the ones: single capacitor, parallel capacitor, and series capacitors. And each of them okay. I figure while I talk about the circuit that I set up, I might as well start measuring because it takes some time anyway. So the circuit that I set up are 3 capacitors of my choice. These here, and there are 470, 220, and 100 microfarad. And then because they're relatively small, I chose a large resistor of about 100 kilo ohms. And then I put these 3 here in parallel to each other. That means also I almost ran out of connectors. And then, as you noticed, I just started charging the capacitor and started measuring right away. And that's what I'll be doing for 150 seconds here. So every 10 seconds I read off the voltage. I don't know if this shows up on film, but at least you can see the setup, the circuit, the timer, the multimeter, and the computer here where I enter the data right away, so that way you don't have to write them down and then enter them later again, but I only have to do it once and then just copy paste the data into the lab sheet. Okay, almost done here with charging, just one more. Alright, now I've charged this one, and now I will discharge it. Again, I almost ran out of connectors. Alright. And here we go. So in my example, I figured I'd do these 3 in parallel to each other. Now, that's what I also said earlier when I introduced my circuit, so these are definitely parallel. And I'm measuring the charging and the discharging on this circuit for 150 seconds each. And then you would have to do the same thing for them being, for your capacitors being in parallel and in series, and then each single capacitor, respectively, that's what you're going to start with, each single capacitor. Both charging and discharging for a total of 8 data sets that you're going to evaluate on in Excel. Which pretty much means that you're gonna enter the data and then actually let Excel do most of evaluating the data. Now twice 150 seconds is of course 5 minutes, and I'm virtually done with that. I'm talking, actually I didn't miss a data point, but if you missed a data point, that's okay, just leave it blank then. You don't have to start over again, you just deal with one fewer data points and the analysis will still work out as long as the data are good. Alright, and here we go, and I can stop that, and if I really wanted to, I could discharge my capacitors, and there it goes down to 0. Alright, and then I got my data to evaluate.
This is the analysis of the example data that I took, and here they are for charging, and here they are for discharging. Over here I'm gonna put these numbers in first here. This is kind of like a default value. I explain that later on. I like to leave it about that, about 3.55 volts or 3.5, something like that. And as I said, I'll talk about it in a little while. This one here I said was 100 kilo ohms. I measured it and it came up to 99,000 ohms. And then I said I took these three capacitors, 440 microfarad, 220, and 100 microfarad, and I put them in parallel. And down here, for right now, I pretend that I don't know what happens to the capacitors in parallel, and of course you as the student wouldn't know that necessarily. If there were resistors in parallel, then we would know that those resistors would add as the reciprocals. But these are capacitors. Maybe something else is happening. Because I don't know what the expected total capacitance is, I also don't know what the time constant is. Okay, so let's go ahead and start analyzing those data. So I'm going to grab all of these here, and I can just, once I put them in here, I can just do Control C for copy, and then I go over here, and here is the Excel sheet. And notice there are no data. Obviously at this point I'm going to paste them in just a moment. Here are the graphs for charging a capacitor, and here's, I explain that second graph here in a moment. Anyway, I'm going to paste this one in here, and then it automatically graphs it all, and pretty much the analysis for the most part is actually done. There will be one little thing here that we have to fix in a moment. Okay, I'm going to grab the other data actually for the discharging. So there we go, and also here was just a little bit off the screen. It also graphed all the data right away, so pretty much a lot of the analysis is already done by Excel itself. Alright, this one here is the typical graph for charging a capacitor, so that the current that flows through it charges it up relatively quickly, so the voltage goes up relatively quickly, but the closer it gets to the top voltage, the more it slows down. And basically the equation that describes this kind of graph is 1 minus the exponential, and you see that in the lab sheet. And now the problem arises that Excel cannot evaluate that kind of graph. I'm sorry, that kind of formula or graph, yeah. So therefore, I put the second graph here. This is usually how you don't see charging a capacitor graph in literature, but that's what I had to do in order to actually analyze those data. So pretty much what I do is I choose a voltage right here, that's the 3.55 I talked a moment about, and I subtract my data from that 3.55, and I think you can see that here, that 3.55 minus 0.36 is 3.19, 3.55 minus 0.64 is 2.91, and so on. So that's what it does. Okay, so again, the idea is that this one here this one is the normal graph for charging a capacitor, but Excel cannot analyze that kind of equation graph formula. So I have to use this other one, which is just a typical exponential, and that's what Excel can do. Okay, in any case, I do actually have to adjust something. Here I put 3.55, kind of like a benchmark default value, but here it says actually 3.22 volts when it goes in and analyzes the data. These two here, this value and this value here, have to be adjusted to each other. So what I'm going to try to do is I'm going to plug in here 3.22 and see what happens. Also note, oh yeah, and before I do that, notice that the line here is not nicely on the data, right? For the discharging here, it goes nicely to the data. This is pretty much done, but for the charging it's not. So I need to adjust the voltage here, hit enter, and then so I put in 3.22 volts, but notice I come up with 2.96, so still not right there. So I'm going to try 2.96. Okay, still not there. This time around I'm going to try 2.80, and what I'm doing here you probably have to do also, so you have to go forth and back several times. That's one actually much closer, 2.8, 2.75. So 2.75, so you have to go forth and back here. Ooh, this is really close, and I believe I'm just going to leave it at that. 2.75 here, and here 2.7465, which also is around at 2.75. And we can see that the line is, the exponential trend line here is nicely on the data, and it gives this regression coefficient. The regression coefficient tells us how good the data are. The closer it is to 1.0000, the better the data are. In my case, I actually do have a 1.000, so my data are virtually perfect. Here on the discharging capacitor, you can see the regression coefficient is 0.9999, very close to 1 as well. So again, the data are very good as well, almost perfect, and that's likely what you're gonna measure as well, is very good data that the trend line nicely fits in, and the regression coefficient tells you that. Okay, so now I'm actually done with this part here, readjusting the voltages. Now I'm going to go in here, I'm going to do 99,000, and then I guess I accidentally forgot to make some space here for the other capacitances. So I have 470 here, 220, oops, 220 and 100, and they're all microfarads. And again, I still don't know what I should expect with these here being in parallel. Alright, now what I'm going to do here is, so this one here, Excel has analyzed the data for me. I'm going to look at this one here, so the 2.7465 fits nicely my 2.75 over there. And now I'm going to look at the exponent, and that's what I need. The 0.134, I don't need that negative, just a 0.134, which is the exponent right here. So I'm going to type it in here. This is for charging. And the exponent is the reciprocal of the time constant. I'm sorry. Yeah, it's a reciprocal of the time constant. So when I hit enter, I come up with a time constant of 75 seconds. And then the time constant is going to give me the capacitance as well. Take the time constant and divide it by the resistance, and that comes out to around 800. Here I do have it's hidden in here. I do have Excel rounded to the closest 100. So it's either 800, 700, or 900. Comes out to 800. Now I'm going to do the same thing over here. For discharging, it says 0.127 in the exponent. So I'm going to plug that in here, 0.127. There we go, and it calculates a time constant of 79 seconds and a capacitance of 800 microfarad as well. So actually, again, that's rounded. Notice that these numbers are slightly different here, but rounded then comes out pretty much to the same thing. Okay, at this point, I could look actually at my 3 capacitors that I used in parallel, and I can look at these 3 values and compare to what I actually got and figure out that, well, very likely in parallel, capacitors are simply added. So while resistors in parallel, the reciprocals are added, capacitors in parallel are simply added. So 470 plus 220 plus 100 is going to come out to 790. That's what I should be expected with an RC time constant, which was calculated right away to 78 seconds. All right. And that's how the data are analyzed. You saw the recording on how the data are taken in the RC circuit, and you saw this recording on how the data are analyzed, and I don't think that's really a big deal. Seems a little bit overwhelming to begin with, but then after all, it's just paste these data in here. Excel is doing all the work for you on discharging a capacitor. All you have to do is grab that exponent and put it down here. For the charging, again, it's doing all the analysis for you, and the only thing you have to do is go forth and back between the voltage over here and the factor in front of it and try to adjust them to make them as close as possible to each other, and then again grab the exponent and put it down here. Okay, just one little thing, kind of a side note. Notice the times that I put on here, 0 to 15, and I put in parentheses that these are each 10 seconds. So this is actually 50 seconds. Same thing here, 50 seconds, 100 seconds, 150 seconds. And the reason I had to do that is so that my exponent, that I get one more decimal on my exponent, because otherwise it would have read 0.013 and I would lose that last decimal there. So that's why the scale, the x-axis here, looks a little bit strange. It just, the reason again is that it gives me one more decimal. That was just a side note. And with that, I'm done with analyzing. No, actually not quite. I actually just want to copy these numbers and everything in here, so I'm not quite done. So this one here, now I know I would expect 790 microfarad and 78 seconds. And here Excel figured out for me that it's 800 microfarads, 75 seconds, and 800 microfarads for 79 seconds. And I don't need to write down the exponent here. That was just an Excel to help me analyze the data. And then what I do is I paste the graphs in here. And there we go. Charging and then discharging and the analysis of the data. And now I believe that's it for this analysis. Okay, this is my recording for drawing an RC circuit, a discharging RC circuit with 3 capacitors in parallel. And when I'm done, it should resemble this one here, except it has a 3rd capacitor sitting over there, and then with the resistor in series, and then of course a switch, and then instead of having the battery connected, I would have to bridge it over here and disconnect the battery, and then they would be discharging. So here we go. I'm gonna draw this sideways because it fits better on this canvas. So here's my battery. Probably using a couple of AA batteries, and then here are my capacitances, my capacitors. Put them perhaps over here. I don't think I need the name really. I'm just going to call them. Let's see. According to my example, I believe I used 470 microfarad. I'm going to try this again because a moment ago it gave me a nice micro there. So let's see if I do this. And then I do 470. Maybe it's going to keep that as a micro. Oh, nice. Okay. And then I believe I used 220 in my previous example. Let me see. Is this my... Oh, now I lost my example. Can't believe it. I saw it earlier. Ah, there it is. Okay. Yeah, 470, 220, and 100. There we go. All right. So let's see, that's how they look like. And now I still need a resistor. Need to turn this one here. There we go. Oh, and this is a large resistor. Let's see, the one I used. Oh, mine was actually 99,000. I used, and I put that one in series with these. Then I'm going to use a switch. There it is. And then I connect these there and there, here and here. And if I left it as such, now I would have actually, and then I close the switch. Now I would have a charging parallel capacitance circuit, but I'm supposed to draw a discharging one. So I'm going to take this lead off. There we go. And I'm going to take this one off. So I disconnect the battery and then connect from here to here. And then, oh yeah, and I think I need a voltage source. Voltage or current, one moment. Definitely a voltage source. So I need to grab it probably off the picture. So let's see where to go. Ah, there it is. Okay, and that needs to be in parallel because I need to, that's just because I need to measure the voltage of all these capacitors together. And there we go. There's my circuit.